Did you use AI?
No.
Did you use macros?
No.
Did you use emmet?
Yeah.
Okay, that's a macro.
Well, I don't know if we're talking about the same thing, but the thing that just allows you to add numbers in the editor.
Like you like type a shortened thing.
Oh.
Like
okay.
P tab.
No, I wasn't using
creates
that.
a paragraph block. All right. Anyway, so welcome everybody to our 11th lunar Zig meetup for the year 2025. Thanks everyone for coming. Thanks Vivint for hosting us and providing the pizza. Thanks to Jeff for reserving the space for us. And we're going to go ahead and turn the time over to Niles Salter to talk to us about a giant u32 map in Zig. And with that, it's off to you.
All right, thank you. Are we live now?
We are live, yeah.
Awesome.
It's
All right.
streaming and it's recording.
Okay.
Your A is you went hard on the border there.
I did. I wanted to take up as much of the screen as possible, so hopefully this gets my point across.
That's like giant.
Yeah,
Oh,
definitely.
okay. I see what's going on.
Yeah,
I get
it's
it
a giant map, you guys. All right.
Okay, I get it now. I get it now.
Should I wait for Andrew?
He chose to do what he chose to do.
And
He's
he's
got to live
already
with the
saw this
consequences.
Okay. All right. So the problem that we'll be solving tonight is mapping IPv4 addresses to their index in the set. We have 160 million of these. And in IPv4, we're going to be representing as a u32. And basically what we're trying to do is figure out, we're basically doing something that's equivalent to a minimal perfect hash function over those u32s. So that's what I mean by we're mapping it to some index. That way we can have a packed array of associated data, and we can use that index to look up whatever data we want. So naively, the way that you could solve this is you could have a sorted array of u32s, and for real-time queries, you could use binary search. Now, without any compression, this is the best you could do for a map implementation in terms of memory consumption. If you use an off-the-shelf hash map out of the standard library, it's going to have an index in the database sense, which is going to speed up queries through some other mechanism. And that's kind of what I'll be talking about here. So yeah, this would take a minimum of 640 megabytes if you wanted to store all of those keys. So we want to do something that allows us to compress the keys. Yeah, a smart hash table index would only make this worse. So the first technique we can use is instead of storing each IPv4 as a u32, we can save memory by storing 2 to the 32 bits, which represents the entire universe of possible IPv4 addresses. To indicate that a particular IPv4 is in the set, simply find the bit position corresponding to the IPv4, encode it as a u32, and set that bit to 1. Okay.
Wasn't it Bill Gates who said we never needed more than 640 megabytes?
Yeah,
Kilobytes. It's
Oh,
kilobytes.
yeah.
So we're already over that with this.
That was the 8.5
Yeah.
floppy disk.
Yeah, so 2 to the 32 bits is about half a gigabyte.
5.5.
So yeah, this is half a gigabyte just to get started. So here's a basic example. Let's assume that we have IP addresses that are U4s. That means we could represent the entire universe of possible U4s with 16 bits. And the idea is the same. We go to the bit at index 2, and we can set that to 1 to say IP address 2 is in the set. IP address 6 is in the set. 8 is in the set, as is 11 and 12. So we also want to associate some data. Let's say it's this array. The first bit maps to the first one. The second bit maps to the second one. I think you see where this is going. So the index that we want to map each subsequent IP address to is now underneath the 1-bit. So let's say that we get a query for IP address 11. How would we actually figure out that 3 is the correct index for it? Well, we can start by doing 1 shift to the left by 11. This is going to be visually right because I'm showing the least significant bit on the left-hand side. So anyways, we can subtract 1, and this will produce a mask for all of the bits up to but not including the bit we're querying for. We can then do an AND, which will preserve the bits under the bit we're querying for. And, fun fact, on x86, everything that I've shown thus far can be done in one instruction. It's the BZ high instruction. We feed this into a pop count, and this tells us how many 1 bits are there in this bit string. And so this gets us to the correct index, which we can then map into an associated array. So does everyone understand the basic concept of what we're doing? Go ahead.
That's very cool.
Yeah.
We go back like 2
So
slides.
does the this is a single instruction, and it counts up the 1 bits after the AND? Or is
Yeah,
that
so
2
BZ high,
instructions?
it will take in 11, and it will take in the bit string,
Okay.
and it will keep the bottom 11 bits.
So whatever you put in, it's doing an AND on the lower bits, and then counting up the ones that are essentially in there. So it doesn't matter where they're placed, it's just a count, and that count.
Yeah, we feed that into a pop count, and yeah, it's always going to be bits that come before the bit we're querying for. Obviously, these 2 bits were deleted. So yeah, do you understand this, AJ? Or is there something I could explain better?
Okay, so first of all, for the first couple minutes, I was still dealing with some streamy stuff. So I missed
Okay.
the
So-
first slide or 2.
Yeah.
I don't understand why 3 was important here.
Okay. Let me back up a little bit. So we have a universe that represents all possible U4s. Okay. And what I'm saying is
It represents all possible U4s, and
Yep.
that was supposed to be
that's this
because-
bit string up here.
But are we still talking about an IP address?
We're talking about a giant map.
Yeah, so first I'm talking about a mini IP address. If we imagine there were only 16 possible ones, just so I can show you on one slide, a 16-bit universe. So you can represent any number of unique U4s, like as a set of U4s, in a 16-bit bit string, and that's what we're doing here. And so I'm showing this would represent IP address 2, and 6, and 8, 11, and 12. Do you get that? If we're talking about a U4 world.
Okay.
Okay?
So where are the spaces supposed to be in those numbers?
So what this represents, so we have 16 bits here.
Okay.
This first bit tells you whether IP address 0 is there. The next one tells you whether IP address 1 is there. The next bit tells you whether IP address 2 is there, right?
And then are we going next to 4 or are we going next to 3?
3 will be right here, 4 will be right here. And so the idea is we're going to scale this up to 2 to the 32 bits because you can represent an IP address as a U32, right?
Yes.
An IPv4. And so yeah, when we scale down to a U4, the idea is that each bit here represents a successive IP address that is either in the set or not in the set. If it's a 1-bit, it's in the set.
Okay, so we're saying that you just take a very long bit string. So if you have 16 IP addresses, you have 16 bits.
If you have 16 possible IP addresses, then you would need 16.
Right, if you have 16 possible. So if you have 4 billion possible IP addresses, you just need a cool 4 billion bits, which is pretty easy to come by today.
Mm-hmm.
And that's way more space efficient than storing each individual IP address.
Yeah, I'll show you the numbers on this as well.
Okay, so and this lets you know if it's in the set. Okay, all right. Now I'm starting to track. I think I'm caught up.
You can get those bit streams at Walmart, but you have to get the right brand.
Really?
And yeah, so we're associating each successive one with a successive index in the array.
It's a sparse array.
So I don't understand why it's called ABCD.
So that's just random data that we might be mapping to. So
It might be the actual address.
so yeah, what we actually use this for at work is to map to some kind of like profile number, and so this would be like a U16 or something that would.
So are we
Puts you in a
saying
category.
that we are mapping to, so we're saying we're just counting the ones because whatever position we find a 1 at, that's going to end up being in our array that stores the data. That's our index into the array that stores the data. That's where this is coming up.
I think you get it. Yeah.
Okay, all right. Oh, feels good.
Okay.
Yeah, this wouldn't have to be IP addresses, it just has to be something that's,
Could be any U32 if we're talking unique U32s that can be sorted. This is also sort of a static data structure in many ways, because I mean, yeah, if you wanted to add another one in here, you could, but then if you have a packed array that you're mapping to, you'd have to make room, you know. So yeah. So this is the basic idea. I think everybody's on board with this now. So here is the Zig code for this. We have this query function, and I have this number line looking thing. So what this represents is all possible 2 to the 32 bits. Yeah, so 2 to the 32-bit bit string. The vertical lines represent checkpoints. And so the basic idea here is if I have a query that is somewhere in the middle right there, I don't want to have to count how many 1 bits there are for all of the bits, right? Because this is like half a gigabyte. I wouldn't want to have to go over half a gigabyte's worth of data. And so I have this checkpoint system, which is just an array where I can take my IP address. Oh yeah, I have the line of code here. So I say, if the bit is there, then we're going to do something. If it's not there, we return null because it's not in the set. In this case, we assume that it is. So we can take the most recent checkpoint bit position. We have our IP. We can use this align backward function, which is a little cut off. Oh, there we go.
Yeah, I thought you were being a little aggressive on that.
Yeah, I know. I'm being kind of aggressive on the borders here. Okay. So this will get us the most recent checkpoint bit position, and we can map it to a checkpoint. And this checkpoint is going to tell us how many 1 bits there are up to the position that it represents. And the checkpoint interval that I've chosen here is 2048 bits. And so I'm effectively, we could have also just done IP divided by a checkpoint interval, and as an integer division, it will round it to whatever the last checkpoint was. So this means that this highlighted region here is all we have to look at for a real-time query if we pre-process the structure such that we have checkpoints. So hopefully everyone gets that.
So we are, for each chunk, we're going to count, and then we're going to store in a separate place which are the chunks and how many are counted up to that point, so that when we get to a particular point, we just, so, okay.
So are you doing presence on the whole string or just on individual chunks at this point?
Yeah, so we might get any query for any IP address from 0 to 2 to the power 32 minus 1.
Right.
And so the first thing we want to do is we want to divide that by 2048. That's just an interval that I picked. And that gets us a slot in an array that we can look at, and we can say, what were the number of 1 bits up to this checkpoint? That means that in real time, I only have to look at this gold highlighted region between, the checkpoint. I just have to look at the checkpoint that I'm in. So from the last one to the next one, I have to look in there.
So when I think of when I'm thinking about IP addresses, I'm thinking about 4 octets.
Mm-hmm.
And when we're thinking about it this way, we're thinking of it as an index 0 through 4 billion and some change.
That's correct, yeah.
So
We're just ingesting it as a U32.
okay, so when I've got my IP address, which is kind of hard for me to think about IP addresses as sequential number, because I'm like, I do IT. I'm used to the dots and that. I know what an IP
Yeah.
address is. I know how it routes. I know what the net mask is. Okay, so help me.
Yeah, so you have 4 octets.
Yes.
You turn each one into a byte, and you concatenate them. That's a u32.
Yeah. Like, I get that part.
Okay.
But then what we're saying is that in order to know if that exists in the set,
Mhm.
because we want this the big uint32 or the giant uint32 thing, as we're talking about. That is whether that's a presence check. But we wouldn't want to take up all that space for our array because it'd be so much wasted space, even if it was just a pointer, that'd be 8 bytes for every single bit, which would just be untenable. So instead, we are...
Yeah, that would be like 32 gigabytes to store it that way.
Yeah. So instead, we're just storing this one thing that's maybe 4 gigabytes, if we're doing the whole internet, and then from the ones that are present, they're in an array.
It'll be half a gigabyte because it's 2 to the 32 bits. So it's 2 to the 29 bytes. So it's half a gigabyte, approximately.
Wait.
Does that make sense? So if you have 4 billion bits...
Oh, right, okay, I'm with you. Okay,
if you go to
right.
bytes,
So, right,
yeah,
okay.
it's a
right.
factor of 8.
Thank you, I understand, okay. So then we are...
Oh.
Whoops. So we are trying to find out if this thing's there, and in order to do that, we know what position it should be at,
Mhm.
and then we're just saying, go to the segment that's the position it should be at, and look at, for that segment, how many ones come before it,
Mhm.
and then how many ones are up to this point, and then that gives us the index into the real array that has the struct with the data.
Mhm.
Okay, I'm tracking.
Yeah,
Forgive me for
I think
being
you
the
got
slow
it.
guy in the room, but
Totally fine. I'm just confused with one part of this.
Sure.
Isn't const at vector checkpoint byte interval U8 already a line 1? Or is the line 1 referencing the pointer that you're using? Like, can't you
no.
remove the line 1? Because U8 is already a line 1.
No, this would have an alignment of whatever this vector's alignment is, which
Oh,
I
okay,
th-
I see.
I think, I actually don't remember off the top of my head what
I
it
just
is.
thought it would
But
take
you do have to
on-
override it to be a line 1, because it's normally larger.
Got it. Yeah, so I thought of the vector as larger, but I didn't realize it would take the full alignment of the vector and not quite
Mhm.
use.
Yeah. Let's see. Okay, checkpoint byte interval is 2048 divided by 8. So we're talking about 256 bytes. Okay. So we go grab those 256 bytes, which, yeah, in this case, I'm just choosing to stick it in a 256 byte vector. And I also pull out the local position of the IP address in the checkpoint using this. So I'll go over what this does real quick. I don't know why I chose to write it this way. I probably wouldn't write it again this way, but this will create an unsigned integer of 2048 bits, and then we pass this into log2 int, which will give us an integer which is the base 2 log of 2048 minus 1. And so this will give us an 11-bit integer. Again, I don't know why I wrote it this way, but yes, we truncate our IP address to the bottom 11 bits, and that tells us within the checkpoint that we're in where we are in that checkpoint. Okay. Next, we have this HHIDs array, and that's the associated array that we're looking up in. And yeah, we're going to be adding whatever we got from the checkpoint to whatever is the pop count within the checkpoint, stopping at this many bits. So we're going to find out how many 1 bits are there before the bit we're querying for in the checkpoint, prior to the bit we're querying for. Anyways, I hope that makes sense. So we're going to zoom in on the checkpoint now, and you'll note there are 32 of the dashes or what have you. These represent 32 U64s, 32 8-byte values. 32 8-byte values is the same as 256 bytes. It's the same as 2048 bits. So I'm not playing any tricks here. We have the vector and we have the position we're at. Okay, so the first thing we want to do, we take our bit position and we divide it by 64, or we can shift to the right by 6, same difference. This tells us which 8 bytes we're in on this line. Okay. We pass this into a BZ high instruction, where the first argument is a bit string of all ones. And this will give us back a bit string, which is a mask of the U64s up to but not including the U64 that we're in. Okay? Now, I actually turn it into 4 vectors of 8 U64. This is because on AVX 512, that's how big a vector is. So you need 4 of them to represent this. Okay, so now we have this mask pop count. We have 4 of these. And the idea is we're going to count how many 1 bits there are in each of these U64s. You can see we're doing it in 4 groups. And we're feeding 8 of the bits at a time into the instruction. I don't know why we have a dictionary on Mac OS.
You did a 2-finger tap by mistake. How big is a 3-finger tap?
Okay,
You can turn that off.
let's do that after.
I agree.
So anyways, also as part of the masking, as I'm sure you probably already figured out, all of the 0 bits here that correspond to some pop count, we're going to zero those out. And this is just using a vectorized pop count instruction that we have. So that's what we're doing. Now what we have is we have the pop count of all the U64s prior to the U64 that we're in. Next we want to add these together. So we can add A plus B and C plus D together at the same time. Then we can pass that into the haddLane function. And what this does is what I just showed. It can take each set of 8 bytes in a vector and do what's called a horizontal reduction, which is basically just what you saw. We just add all the numbers together and we get the result out as a U16. That's one other thing I should mention, is that I'm assuming that these are bytes. The pop counts are bytes. So we can add A plus B and C plus D together, but we can't directly add the result of those together because it might overflow in a byte. And so that's why we do a horizontal add lane first and then add those two together. Okay? Because we're getting the result as a U16. So it will not overflow. And it would have if we didn't, right? We have 476.
So was this representative of the number of ones at each checkpoint? Is that what we're looking at now?
So what we're looking at now is within one checkpoint, there are 32 U64s.
Okay.
Within that checkpoint, we want to know how many 1 bits are there in the U64s prior to the U64 that we're in. 476 happens to be the answer in this case.
Okay. All right. I think I'm following.
Okay. Okay, now we can zoom in on the 8-byte value that we're in. And we do exactly what I already showed. We do a BZ high and we feed that into a pop count. So we mask the bits beneath the one we're querying for. It doesn't show up that great on the screen, but it's this orange one here. We feed that into a pop count. And we can add it all together. So what we just did is, if we return back up, right, we're adding the checkpoint to, so the number of 1 bits that occurred up to the last checkpoint, the number of 1 bits that occurred up to the previous U64, And then within the U64, how many 1 bits came before the bit we're querying for. If you add all of those together, what you get is how many 1 bits came before the bit we're querying for the whole data structure.
Which gives us our index into the array with the real data.
Exactly.
Okay.
Okay. All right, so here's the memory trade-off. Naively, like I mentioned, we could have 640 megabytes to store 160 million 4-byte values. With this idea, we get down about 100 megabytes of savings. Okay. Now, I'm going to show you that we can reduce it by another 400 megabytes using the Elias-Fano encoding.
What?
This is actually close to the information theoretic lower bound of 123.3 megabytes, which I calculated with this expression. Basically what this means is you could imagine if we enumerated all possible data sets of u32s, there are 160 elements within that, so you could imagine the universe idea. If we have 2 to the 32 bits, and we have 160 million of those are 1 bits, how many 2 to the 32 bit strings are there that match the criteria I just said? That's given by 2 to the 32 and choose our 160 million. If we take the base 2 logarithm of that, that tells us the minimum number of bits it would take to distinguish between that many possible data sets. You can imagine if we enumerated all possible data sets and then we have an index into each possible data set, the number of bits that that integer would be 123.3 megabytes. So that's how I got that number, which is pretty cool. We're within 10 megabytes of the information theoretic lower bound, which is pretty cool.
Why can't we get right through it?
I'm sorry. It would be computationally very hard to do that. Yeah. Okay, so what is Elias-Fano? It's a form of delta coding for what they call in the literature monotonically increasing integer sequences. So what does that mean? It means numbers that go up. So imagine this is our set of IP addresses, the first couple anyways. And we're going to split each integer or each IP address into 2 parts. The seal of the base 2 log of n, where n is the number of elements in the data set, that's the split for the upper bits, and the remainder go to the low bits. So because I have 160 million elements in the first data set that I made this for, I'm doing a 28 and 4 split. So what does that mean? Okay, so here are the low 4 bits for each of these decimal numbers. We're going to store those in a contiguous array. That should be pretty straightforward. The high bits, which I've written in decimal form this time, they're going to be stored in what's called an inverted Elias gamma coding. So look at this bit string here. We start with 1 plus 2 to the power of 28 1 bits. And above the first couple here that I chose to represent here, I've written the rank of each 1 bit, which is effectively like its index as a 1 bit, right? Now the idea is we're going to store, after each 1 bit, some number of zeros where the number of zeros is equal to the number of elements in the data set with an upper 28-bit value equal to the rank of the 1 bit. So anyways, here's how I choose to represent that. So this is a symbolic representation. At the end of the day, it's just going to be 1s and 0s. But I've written the decimal number in here so you can see kind of implicitly what we're doing. Implicitly, after this 1 bit that has a rank of 7, however many zeros we have here, it tells us how many IP addresses have an upper 28-bit value of 7. When it comes to these 5 2s, which are going to be zeros at the end of the day, this 1 bit has a rank of 2, and so the fact that we have these 5 zeros after correspond to the 5 2s that are in this data set. Is everyone with me so far? What do you think, AJ?
I think I'm there.
You think you're there?
I'm not sure where this is going yet.
Okay.
But
Well, this is Elias-Fano right here.
how many of each bit are present is how many zeros follow that bit.
Mm-hmm.
Get that.
Okay. So yeah, so this is Elias-Fano right here. I could end the presentation, but this gets you the number that I showed before in the previous slide. This gets you 133.6 megabytes. Okay, so that's actually where this comes from.
Okay, so how is that useful though?
So this is useful because we can actually query this without decompressing the data structure. So you might be wondering, how do we query it?
Yeah, that's what I need to know.
All right.
That's
Okay.
You in the presentation now. The other one I understood.
Okay.
I was like, okay, I'm tracking.
Okay.
Eventually.
So first, I'm just going to define a couple functions. We have the rank function, which has the subscript of b, which allows us to pick either a 1 or a 0. And so this is the number of 1s up to position p, or it could be the number of 0s up to position p. And that's what this rank means. Okay. Are you typing insults right now? Okay.
No, somebody said hello from SLC, and I said
okay.
hello. So we just,
Hello from
we got
SLC.
We got a hello.
We also have this select function. This is basically like the inverse of rank. Given k, we'll find the position of the kth b, which is either a 1 or a 0. So this can be asked, you can ask with this, where's the 10th 1 bit, or where's the 10th 0 bit, or whatever. This is 0 indexed, so it's a little bit hard for me to express in English.
I say once in that case to
Right,
distinguish
yeah.
from first.
Yeah, so the 1th bit, 2th bit, sounds weird, but it is what it is. I also have a special purpose function here. What this is meant to do is match a U4 starting at position P with length K. So this is just taking a slice of the 4-bit array that we saw before and trying to match a particular U4. And I'll show this. So let's say we want to find the index or the minimal perfect hash of a particular IP address. This is the full equation for this. We're going to step through it. Let's say we want to query for IP35. So first we're going to take 35 and shift to the right by 4. That's going to get us 2. Hopefully everyone gets that. 35 divided by 16 as an integer is 2. So this tells us that the upper 28 bits is 2. Okay. Now we're going to select the 1 bit with a rank of 2, which is right there. And that's at position 4. Now we want to find the rank sub-0 of position 4. So that means we're asking how many 0 bits came before it in the whole data structure. The answer is 2 in this case. You can look at the arrow in the bottom left. Then we want to actually go look in our packed array of U4s at position 2. How many U4s are valid is equal to the number of 0 bits above the rank, above the 1 bit that we targeted before. Okay, so because there are 5 directly above the bit that we targeted, that means we have a slice of length 5. And it's going to be somewhere in here. In this case, it happens to be that one.
Now, how did you determine that it was that one again?
Because the bottom 4 bits of 35 are equal to 3. And I've color-coded it so you can easily match.
Oh, okay. All right. Bottom bits. Okay, top bits, bottom bits. Okay.
Okay. So this is what we're doing. Now, when we scale up, we want to build an index in the database sense. And this is a little harder than last time, right? Last time, we knew which bit we were querying for as an absolute position. Here, we're saying, where's the 10,000th 1 bit? So that's a relative position. It's relative to all the other 1 bits. And so we don't know where it is. So how do you actually build an index where you could say, okay, like map 10,000 to like the last checkpoint? How do you do that? Well, I'll tell you.
Oh, good.
I wouldn't expect you to come up with this. So yeah, here's another number line here, and we have different numbers of 1 bits. That's what these numbers represent. So each checkpoint of 2048 bits, let's say we pick the same checkpoint size, we could have a different number of 1 bits in each one. And so the way that I think about it is like the number line on the bottom is kind of stretched out like this. And so if we want to map from a relative position, from a relative position to like knowing which checkpoint we're in, we have to do something a little trickier. What we can do is in the fixed interval number line on the top, what we do is we pick an interval equal to the minimum number of 1 bits in any checkpoint. So let's say that that's 1,000. What this allows me to do is take the IP that I'm querying for, divide it by 1,000, and that can map me somewhere in this absolute interval space. Each one of these is going to map to somewhere that's on the variable interval number line. And this is the data that we're going to get out. It has a chunk index, which tells us which 2048 bits are we in as an index. So the first one will be 0, and then 1, and then 2.
Can one of these not point to 2 of the ones below?
So yeah, this is the next thing I'll say. Because we picked the minimum number of 1 bits for the whole data structure, it's only possible that either we know exactly which chunk we're pointing at, it's the one we're pointing at, or it's the next one. But it cannot be anything else besides those 2.
Okay.
So you can see this 1,000 here.
So you just point back and then...
We're pointing here, but we might also go forward to the next one,
Okay, got it.
based on where we are. And yeah, I made kind of a visual proof here. The upper number line, none of the sections can overlap with more than 2 of the sections on the bottom at once.
Right, got it.
And so yeah, so each one has a chunk index, which is which 2048-bit chunk should we look in? What is the pop count of that chunk? I could also just calculate it on demand, but I had some extra bits. And then what is the prefix pop count up to that chunk? So that's like how many 1 bits are there in the whole structure up to this checkpoint. Does that make sense? Okay, hopefully I didn't lose everybody. All right, so here's the code. I also have the assembly right there. Look at that. I know everybody loves assembly.
God
So
both bless you.
yeah. Okay.
Did you write the assembly first or the code?
I did write it in Zig, but I knew exactly what assembly I wanted to. There's a couple of cool tricks in here.
I'm somewhat of a trickster myself.
Are you? Okay, so I wrote this get index function separate, and yeah, so this, you can see we just get the index, we look it up in the associated array, which is called HHIDs in this case. So let's get into it. All right, we start off with our IP address. We shift to the right by 4 to get the upper bits. First thing we want to do, I put in a blank one here for the assembly. We load in the top bits and the bottom bits arrays. We also load in the HHIDs array, which is the associated data. Okay, first thing we do is we take the IP address, we divide it by the minimum pop count of any chunk. And you can see that in the assembly, this is being mapped to, oh no, did I lose? I lost some of my lines here. Okay.
That's what you get for pushing the boundaries.
I know. Let me see if I can fix that real quick. Okay. Does that work? Okay. my goodness. You flinched me out. All right. So here's what we're doing. We're using basically the same trick that compilers use, which is we turn a division into a multiply, an addition that in many cases is not needed, but sometimes it is, and a shift to the right. It's based off the work of Daniel Meyer. You can see that we calculate it like this. I'm not going to go over it, but there's a cool paper on it. I pulled it from Lemire/fast division. So there you go. So yes, at construction time of the index, in the database sense of the word, I just do this algorithm to figure out how can we quickly, with a multiply, add, and a shift right, how do we do a division? And so that's where this comes from. I don't remember if there's anything else to say about that. Oh yeah, the other thing. So you might notice that I didn't pass in the upper 28 bits, I just pass in the IP. Why did I do that? That's actually a little optimization because right here I add 4 to the minimum pop count in chunk, the right shift right here. So I just add 4 to it, and that way we don't have to wait for the result of that shift 4. We don't have to wait for this to exist. We can get started immediately on this quotient, okay? So anyways, we get the index item, and the index item, as I showed in the previous slide, it's actually a packed struct that fits in a U64. We just pull it out as a U64. It's actually going into RDI in the assembly. So we can take the upper 32 bits of it. That's the prefix pop count. So that's the pop count. Yeah. First of all, do people know what that means, the prefix pop count? Yeah, it's the 1 bits that come before this checkpoint. And then we also pull out the pop count of this chunk. We add it to the previous prefix pop count. We also add 1, and that's just an implementation detail. If you saw on the previous slide, I had a range of 120 to 2048 for this integer, and I wanted to store it as a U11. And so I just subtract 1, and I add 1 when I get it out. So it is what it is. Okay, what index are we in? Index item.chunk index. Should we be in the next chunk? If the upper 28 bits are greater than or equal to the next prefix pop count, then we should. We can then pick which prefix pop count we should be in, and we can also pick which chunk we should be in according to this Boolean. Does that make sense? So we're just picking which checkpoint we're in, which 2048-bit chunk we're in. Then we can compute what is the relative bit we're querying for within this 2048-bit chunk. So that's going to be taking our upper bits and subtracting prefix pop count, just like before. Okay, so now we're going to find the prefix sum of the pop counts for the particular chunk we're in. I do want to show Wikipedia real quick on prefix sum. This is basically what we're doing. So if these are our input, the idea is that each element I in the result array is equal to the elements up to that position in the input. There's also a notion of an inclusive versus an exclusive prefix sum. This is an inclusive prefix sum, and the one I'm showing you will be as well. So does everyone understand what that is before I show how we're doing it? Okay. Now I wrote. You don't get that? Okay.
It's okay.
I mean, look. The point is, 3 is equal to 1 plus 2, right?
Okay. Yeah.
6 is equal to 1 plus 2 plus 3. 10 is equal to 1 plus 2 plus 3 plus 4.
It's kind of some kind of perverse play on the Fibonacci sequence here.
Kind of.
Yeah.
But yeah, the input could be anything, and we would just add those together.
Okay, got it.
Okay. Now, in assembly, if you were to write the one-line version, you would get this very slow routine. The thing that I don't like about it is that we're using all these nice SIMD instructions, but the majority of them are data movement instructions. So what this is doing is it's taking the pop count of all the U64s we have for 4 vectors, and then we are compressing the U64 answers into byte answers. So now each one of these has 8 bytes, which represent 8 pop counts that correspond to 8 of the quads for each vector. Then we have these insert instructions. These are concatenating the vectors together. And so this will get us to 32, I'm sorry, this actually turns it into a 2-byte value. And so we have 32 U16s from here. Okay. And the reason why we're doing U16s rather than U8s to fit the pop count is because when we add them together, we definitely can overflow a byte. Because in 2048 bits, right, you could have more than 256 1-bits. That's why, okay? And so, yeah, these v-align instructions are shift. They're shifting the data, okay? So let me pull this up.
By the way, a little aside here, but how sparse does the data have to be in order for this to be effective? Like, what's the sparseness level at which like this?
So what this was designed for primarily actually was very well distributed IP addresses. Like, so that's what this is running on. But yeah,
What percentage of distribution aside, what percentage of IP addresses are you capturing? And like for example, if you were going to track all 4 billion IP addresses, then you'd
be better off with just an array, right?
Right. And so at some point, this strategy becomes really worth it. And I'm just wondering, like, is it anything below 50% or?
Oh, I understand what you're asking. So, like, what I showed before is that the split that we do is based on the base 2 logarithm of the number of elements in the set. So because there were 160 million IP addresses, that's why I did a 28 and 4 split. Now, if there were, 280 million or so, or maybe more than that, I don't know, that would push us over to a 29 and 3 split. You could also have a 30 and 2 split, a 31 and 1 split, or a 32 and 0 split. At that point, what's the point, right? You could just have a flat array, right? So yeah, it does depend on how much data you have. It turns out when you're in the millions, the 28 and 4 split is pretty good and pretty close to optimal. So
millions or less? Or
yeah. When you have, like, we do have one that only has like 40 million. It technically would be more memory optimal if I did a different split, but I just use the same. I just use a 28 and 4 split for everything right now. If it actually became worth it, then I would go write a separate one or make one that's more generalized. But
if I only had 10,000, I'd be better off just like iterating over the 10,000 and checking them.
Sure. Yeah, you could use a more naive strategy if you only had 10,000. This is for, if you want millions of IP addresses, and in our case, we actually have multiple sets of 160 about million IP addresses. And so we do need a way to do this efficiently.
Making sure people get their ads as fast as possible.
Yeah, exactly.
That's good.
So,
I hate waiting on ads.
I know. I bet you do. Like, what the heck, man?
Actually, I don't know what that's like because I use Brave. But
yeah. Well, so what this is showing here is the idea of a prefix sum. So we take one copy, we shift to the right by 1 and add. We take a copy of those two, shift to the right by 2 and add. And we keep shifting to the right by successive powers of 2, which is equivalent to this, right? And so the idea is that at the end, you can see it's lined up in such a way where this is the sum of 0 and 1, this is the sum of 0, 1, 2, this is the sum of 0, 1, 2, 3, 0, 1, 2, 3, 4, etc. So this is the algorithm that we're performing here. Okay. So we're just doing shifts and adds, okay? Now, what I was trying to explain was, the reason why I don't like this code is because like the bulk of the time that we're going to spend on this is in the shifts, whereas all of the like useful work is pop count and the adds. So the vast majority of the time that we're spending here, these are like 3 or 4 cycle instructions depending on the microarchitecture, and we have a serial dependency chain where we can only do one instruction at a time, and we have to go one by one because there's a serial dependency chain.
Right.
And so this actually makes this algorithm too slow for my tastes. I'm sure my tastes are a little more refined, I guess. Okay.
And a more discerning.
A little more discerning palate than some people.
They won't name names, though.
Yeah.
I prefer to be left out.
Of course, if this were JavaScript, we would just give up. Okay, so so how do we find the prefix sum of pop counts? Let's assume we have a bunch of data here, and we take the pop count of each of the u64s. And so what this represents now is the position. Each letter here represents a byte. The dots also represent a byte, but they're going to be zeros initially because we're taking the pop count of u64s. That's always going to fit within 1 byte. Okay? So that's what this represents. Are you good with me so far? Okay. Now.
And I'm now watching on my
Okay.
phone screen because I don't like the strobe effect that's going on the TV. So I'm still watching, just watching here.
Okay. Next thing we do is we call this combine function. Okay. So what this is going to do is it's going to shift the second vector to the left by 8, the third vector to the left by 16, and we're going to do a 3-way OR, which we can do in one instruction. That's the VP turn log right here. And so this combined 3 of our vectors into just 1 vector. In the assembly, it's ZMM2. Okay, did you see that? I can play it again.
I am not versed enough in assembly to,
So let me explain what we're doing. Each letter represents a byte.
Yes.
It's a pop count of the U64 that was there before. When we do shifts and a 3-way OR, we're just putting that information together.
They're adding it, right?
Well,
not adding it.
We're just putting it into one vector.
Concatenating.
So yeah, we have all the data in one, from 3 of the vectors in one. So we just combine them. That way we can more easily access it. Okay. Next, we return from this function. Okay. So for the next couple of slides here, all I'm doing is I'm showing the compile time code, which gets me this inverse jumble vector. It makes sense if you look at the code more. But yeah, what's the point? The point is I want to be able to express more simply exactly the transformation that I'm trying to do. So I'm passing in this pop counts 0, this vector here. Okay. I'm passing this into a shuffle. And what am I shuffling by? This here. So
what does shuffle mean in this scenario?
Yeah, so shuffle refers to, it's where we want to rearrange a vector. So we're passing in this vector here. This is a vector of indices. And so we can arbitrarily reorder this, this pop count 0 vector right here based off of these indices. And I did that compile time thing so that I can specify it in a nicer way. And so the idea here, just the way that I decided to write it, was the first 8 bytes are going to be zeros. It's actually going to pull from index 7. So it's going to pull from right here. This dot right, I don't know if you can see me highlight it. It's the one right before this B. And so
I
It's-
like how you say before for something that's after, because
Yeah,
you're working
it's
on
flipped.
the alien world.
Yeah, I know. So yes, it's before the B, visually after the B. And so yes, we have 8 bytes of zeros, 8 bytes of zeros. Then we have 8 bytes from the inverse jumble vec, okay? Another 8 bytes of zeros, and this. All right, so let me just do the animation. Ta-da! Okay, so we just pulled the bytes back out in the original order they would be in, but now they are one 16-byte lane shifted visually left, and in reality left as well. But you might think of it as right the other way. But yes. Okay, so we were able to do this with just a vperm b instruction. If you look at the assembly, vperm b takes the vector ZMM2 and it just arranges it according to the indices inside of ZMM1. Okay, so that's all that we did. Now we're going to do a horizontal lane add on this, which I just decided to depict like this. We get some for each of these. Okay, let's move that up. Next thing we're going to do is we're going to shift this vector over by 16 bytes, and then the same original one over by 32 bytes. And if we add those three together, then we get a result which is equal to the it gives us the cross lane, it gives us the prefix sum at the start of each lane for the values that came before that lane.
Got it.
And we're talking about 16-byte lanes. And so what this allows you to do, okay, we do one more shuffle first. This is the vperm I to B instruction. This is very powerful because we can pull from both pot counts 0 and 1. So we're pulling from this top one and this bottom one. And here's what we're doing. We're just going to put them back in order, but we're going to interlace zeros. So that looks something like this. It's a little choppy on the TV, but okay.
It's smooth as butter on the screen.
Okay. So yes, it just puts the bytes back in order, and then we can add these two together. And what we've now achieved is a situation where if we find the prefix sum within each 16-byte lane, that will give us the correct global answer of the prefix sums in total. I apologize for the representation here with how...
As you should.
Yeah, I don't really like how that part turned out. But anyways, the idea is we're going to shift left by 2 bytes and add. Shift left by 4 bytes and add. And shift left by 8 bytes and add. Okay. And this will get us the correct prefix sum for the whole 32 U64s pop counted. Okay. So when we return this, we have now computed the prefix sum of pop counts. There you go. That's the most efficient algorithm to do it on AVEX 512, probably.
That's insane. Because in data science, you basically invented faster convolution.
You were sleeping for like the last 10 minutes.
No, I watched the whole thing, but
You were snoring.
was that?
Yeah,
Because I pretty much remember from the start what you did.
he was snoring. He was snoring. I guess I have a soothing voice. I don't know.
Here I am struggling to keep up. You sleep through 10 minutes of it, wake up and have meaningful commentary.
Well, I don't know. In my head, I was trying to follow how he's doing this and how this is going to help Ed. So I was kind of starting from that ABC backwards to where he was starting from. Trying to figure out how to do it. And yeah, it's kind of insane.
All right.
I'm going to steal that code to do.
Go ahead.
convolution.
I don't know if it will help for convolution.
Well, what you did was a convolution, just with instead of like floats. And if I convert my data to integers, I feel like that's faster.
You can certainly try. Okay, so we take the bit that we're querying for within this chunk, we splat it into a vector of 32 U16s, and yeah, this A, B, C, D, E, F, G, right? This represents the prefix sums vector. Okay, so that's what this result represents. So we do the compare less than unsigned 2 byte granularity instruction, and that gives us this bit string. Okay. So what does this mean? It means that we are in the chunk corresponding to n. Okay. Now, we want to know how many 1 bits did we skip over to get to n. What's the answer to that, AJ? It's going to be in M. So these represent pop counts. It's a prefix sum pop count. So this is an increasing array from right to left. And N represents where we are. M is the one right before it. And so what we want to do is we want to extract M, and we want to subtract it from SEL, select, within this current chunk. Okay? So how are we going to do that? We're going to shift visually left this vector, shifting in a 0, so that our mask now lines up with M. Okay? Now we can feed this into a vector compression, which keeps just the elements that correspond to a 1 bit, meaning it's going to keep M and beyond. When we extract the bottom value at index 0, that gives us M. So this tells us how many bits did we skip over. Okay? We can then subtract how many bits we skipped over So now we know within a U64 which bit we're querying for. We can take the count trailing zeros of the mask, which is just count how many zeros there are right here. And this tells us which U64 in the chunk we are in. We can then look that up. Let's say that this is what the bit string looks like. I'm using dots for zeros here just because it looks nicer visually. And let's say for this example, the 1 bit that we're querying is at the very end. So this is the start over here. Okay. This is the least significant bit. Over here is the most significant bit. Okay. So first thing we can do is we can do 1 shifted to the left by the bit the 1 bit's rank that we're looking for within this U64. We pass this into a PDEP instruction. Okay. Now a PDEP instruction does what I just showed. I'll explain it in English. Each successive bit in here is going to map to a successive 1 bit in here. Okay. And so you can see that we're spreading out the successive bits on the bottom operand such that they line up with the 1 bits on the top operand. That's what PDEP does. Okay, so that means that this enables us to pick, for whatever bit we're selecting, we can pick that 1 bit. Okay, so if we were picking out the 1 bit with a rank of 0 locally, it would give us this first one. If we were picking out the 1 bit with a rank of 1, it would give us this one. If we wanted the 1 with 2, it would be there. 3 would be the next one. 4 would be this one, and so on. So that's what we're doing. We're just figuring out which 1 bit are we targeting. Next, we do this big equation here. It might sound scary, but actually what this is doing is we figured out the absolute position in the bit string, and we also know how many 1 bits there are up to that point, right? Because we just asked, where's the 10,000th 1 bit? And so I know there's 10,000 1 bits before it as a 0 indexed thing. And so I know how many 1 bits are before it. I just found out what the absolute position is. How do I find out how many 0 bits came before? A subtraction. And that's effectively what we're doing here. We're just subtracting the absolute position minus the number of 1 bits in the whole structure. So yeah, if you want to dissect that, you can, but I'm good with that. We can also do prefetch if we want to get started on loading the answer at the end. We can do that right now. Okay. So there's a problem, which is the next thing that we wanted to do was we wanted to find how many 0 bits are there immediately after the 1 bit we're querying for. Now, it might actually run off the end of the u64 that we're looking at. So imagine that this is the next byte, or the next 2 bytes. And hold on a second. There you go. Yeah, so imagine this comes after, right? We want to count how many zeros are there immediately after this 1 bit. And so we need some...
And after, in this case, you're speaking, again, right to left?
Yep.
Okay.
Yep.
So after means
Right
closer
to left,
the
yeah.
left side of the screen.
Exactly. Yep.
All right.
So yeah, so we need some technique to handle this problem. And this could happen anywhere, right? If we were selecting this bit, we want to know how many 0 bits are right here. But yeah, there's a problem that could happen, which is if we're at the end or close to the end of our bit string, then we need to find some extra bits. So you're going to need a minimum of 2 extra bytes, because if we're at the end, I don't know if I should say minimum there. That is the minimum you need to be guaranteed to get all the zeros that you need. So yeah, because there are 16 possible U4s, the maximum number of 0 bits there can be contiguously is 16, because we have a unique integer sequence. However, you can see that I just load in the code here, I'm loading 32 bits anyways. The reason for that is because I want to guarantee that there's a 1 bit in this second chunk that I load. Okay. So here's the algorithm I came up with to solve this. It's only 3 instructions, which is pretty cool. We take the count leading 0 of the isolated target bit string, which is this one right here. So count leading 0 gets us, can you count that for me, AJ?
2.
2, all right.
Thanks for giving me these.
I know, I need you to.
appreciate
Okay, so the next thing we do is we're going to do this shift left instruction. So you can see in the Zig code, I bitcasted chunk u64 followed by chunk u64-2 to a 128-bit integer. If I take this 128-bit integer, I shift it to the left by the count leading 0, and then I shift to the right by 64. That means take the upper 64 bits of the result. Okay. That's going to look something like this. I'll show the animation if you're looking. Ta-da! I don't know if you saw that. Let's do it again. Ta-da!
Oh, I missed that
Okay.
because
You missed it again?
somebody had some very important and unsafe comments to make, which I will make slightly safer for the purposes of our unsafe meetup.
Okay.
Is it possible to be a SIMD god?
You know, you don't need to finish the sentence. I actually, I know what the rest of the sentence is. We can go over that another time.
You know the rest of the sentence?
Yeah, it's my friend messing with me. He's messing with me. So, okay, so what's the point? We do a shift left D here, and this is going to, what this is going to do is it's going to take all of the bits that are after the bit we're querying for, and shift it into this second bit string we loaded. Okay?
Due to the
Yeah.
Harry comment,
I know you're a little distracted.
I missed.
All right, so let's do
I
it
missed
again.
like a sentence.
Let's do it again. So shift left D is like a shift left, except we're shifting in the contents of another register or another value. Okay. So how much do we want to shift left? It's the count leading 0 here.
I don't want to shift left anymore. I'm done.
All right.
I'm done
So
shifting
we're
left.
shifting in the values that are above the target bit. But it's actually based on this bit string here. So if we were further in, let's say our target bit was right here, then we would shift all of this into this upper bit string here. Sorry, it's a little hard to select. Okay. Then we could do a count trailing 0 on that result right here to know that there are 5 0 bits immediately after the target bit. So in 3 instructions, this is a way of branchlessly computing how many zeros are there immediately after the target 1 bit. But yeah, by the way, no branches anywhere, okay? We don't write branches here, okay? So anyways, okay, let's actually go look at the array of packed U4s. So let's take our bottom bits index, which we computed, like I already said. We have to divide it by 2 or shift to the right by 1 because we have byte addressable memory, but we have packed U4s. So there are 2 U4s per byte. So we have to divide by 2 to map our index onto bytes. Does that make sense? However, as I'm showing here, we might not get the one that we were looking for at the start. By start, I'm talking about right to left. So yeah, we might have 4 bits that we didn't want. Maybe we wanted to start here, but we got this anyway. So how do we rectify that? I have this here. We can grab the 8th byte. And then we can do the shift left D trick again, which is we shift in 60 bits from here. You can see that they line up diagonally. Okay. We shift in 60 bits from here. And this gets us the 2 possible things that we're interested in based off of the bottom bit of our index. Okay. So if the bottom bit of our index, you can see it selects it there. If the bottom bit of our index was a 1, then we want the bottom one. If it was a 0, we would want the top one. And this would actually have the information we're interested in. So what's the point? The point is we're going to grab 16 4-bit values, and yeah, that's because the maximum number of 4-bit values that could be a candidate is 16. That's because the number of possible 4-bit values is 16. Okay, so we just load in a 64-bit integer, like just our normal register. We load it with 16 U4s this way. We select one of them, which, yeah, in this case I showed we're picking the bottom one. And then we say, what's the lower 4 bits of our IP address? Let's say that it's this number here. That would be 12 in binary. And we have this bit string here as a constant. We can multiply those 2 together, and this will do this. So the point is we just broadcasted this 4-bit value 16 times. Does that make sense? So we have 16 copies in the result here. Does that make sense? I didn't put the multiplication symbol, but we're doing multiplication. Hopefully you get that. Next, we're going to do an XOR with the slice and the value we just broadcasted. Okay, that's going to get us some result. Now, the interesting property of XOR here is when you XOR 2 things that are equal, you get out 0. When you XOR 2 things that are not equal, you get out non-zero. So you can see here, this value was the same as the one that we're looking for, And so we got out 0 in that nibble. We might also see the same one somewhere else. You can see these ones matched. And we got 0 here as well. Okay. Okay, now we're going to want this constant. And we're going to do 2 and nots at once. So I'm going to go over this slowly here. So this value, and we do an and not with this one, okay, that is going to preserve the bottom 3 bits of each nibble, which is half a byte, and delete the top one. Down here, we're doing the same and not, but with the arguments reversed. This, ANDed with the not of this, is going to only preserve top bits, because that's where we have bits in here. And it's going to preserve the not of whatever we see in the bottom here. So because you see a 0, that gets flipped to a 1. Because you see a 1 here, that gets flipped to a 0. Okay. You see a 0 here, that gets flipped to a 1. You with me?
I think so.
Okay. Now,
I have lost the context of why this is important,
okay.
by the way.
So what we're doing is we're trying to find which U4 we match. So this happens to be the answer right here. So we want to know which of these nibbles we match. Could be multiple, but we want to know the first one. And we already computed how many of these are valid to look at.
But what, I got a little lost too. Why
Sure.
are we wanting to match which nibble?
Sure.
Why do we want to know which nibble we match?
Yeah. So we had an IP address which is 32 bits. We took the upper 28 bits and we found which slice of nibbles, like one of these might correspond to our IP address. We want to find if it's in there. And if it is, we want to know at what position it is. And so in this case, we got 0, 1, 2, 3, 4. So this is at position 4 within this slice. And so you can see on line 298 here, we can take the bottom bits index, which is where we started. It's right here. It's where we started to read this data. And if we add it to the position that we matched at, then we know which of these U4s we actually matched. And so this gives us what index our IP address is in the set overall. So, okay. Let me think for a second here.
Also, what are we looking at in terms of time for the rest of the presentation?
This is the last 3 lines right here.
Okay.
Last 3 lines of code. Okay, so let me show you in the diagram.
Wait, don't go back.
I just want to show you this diagram.
lines.
Yeah,
Here you
can
go.
we go back to like the 3rd slide and just work from there?
Well, look, I want to explain the answer to the question. So what we do, right, when we take this IP address 35, we find out which bit corresponds to the upper 28 bits, which is this 2, right, right there, okay? Then we figure out how many 0 bits came before it. That tells us where to look in this slice. And here's, and yeah, based off the length that we got is the number of zeros after the bit we're targeting. And so that tells us which slice to look at. Now, this slice has all of the U4s in it, right? We want to know which one of them we are, because this will tell us what index we are in the set. So this would be 0, 1, 2, 3, 4. So this would be the 4th value in the set. We could go look at our array at index 4 for some associated data. So that's what we're doing.
And this is all in the service of essentially a set to know if we...
It's like a hash map, yeah. Or...
Well, a set is a hash map, but
yeah.
with where the items are what you're in. A set is a hash map where what you're interested in is whether or not you have the item there.
Yeah, so not just that, but we want to know the index of it as well.
Yeah, so there's another array. So we're taking the universe of possible values and then we're shortening it, and then we're shortening it again so that we can get the sparse index.
Okay, so it is a hash map, like
Yeah.
hash map property, but
Yes.
trying to be as optimized as possible.
Yes.
Yeah.
So, in here, right, we can see this is 35, but this bit string alone doesn't have information sufficient for us to know that. All we know is that the upper 28 bits correspond to 2. But we don't know exactly which U4 this is without going to go look at the array of U4s. So if we go look, then we can see that this matches, and then that gives us the position. So we know that it's, index 2 plus, 2 after the start, okay?
And, so are we doing this for each nibble, or are we doing this for...
So for any IP address, there's a single nibble that
Because
could
you
match
did a
it.
28-4 split.
Right.
Okay, so the nibble is somewhat arbitrary. It was optimized for your specific use case of doing 160 million
Mhm.
IP addresses. Okay, and other similar sets that are of similar size.
Yeah. Every power of 2, it would change what's optimal, whether you want to do 29 and 3 and
Right.
30 and 2, what have you.
Right, okay, all right.
Okay.
So are you working then with essentially only static IP addresses? Because a lot of IP addresses are not static, they're dynamic and change relatively frequently in general networking.
Yeah. So we do update these caches a lot, but when I consume it in the real-time bidder, it is running on a static data structure. So it's constant for some period of time, but yeah, the data does get stale, and every day minimum, we're generating a new one of these structures.
So, because of the scale of data that you're working with, it doesn't matter that you're getting a bunch of misses because you're just statistically looking for cohorts, right?
Misses in terms of someone's IP changing, or?
Yeah.
Yeah, I mean, in general, IP addresses are stable for some period of time.
Right, but I mean, it wouldn't matter if out of that 160 million, it doesn't matter if 1%, well, maybe 1% is too large, but it doesn't matter if a large number of them,
Yeah, it's not going to be
hundreds
perfect.
or
Yeah.
thousands, it doesn't matter because you're just looking at cohorts of, I'm guessing that your IP addresses are being split into cohorts of some sort, whether that's country cohorts or whether it's preference cohorts, or
Yeah.
whether it's a multitude if you have multiple cohorts that you're pulling from. But you're pulling from cohorts and then deciding, and if somebody's IP address switched and it was a man that had that IP address and now it's a woman and their preferences are different, well, they get a Gillette shaving ad for men. Oh well.
Yeah. Yeah, you just have to live with that. It's not an exact science.
No, it's a very exact science.
I mean, this is, yeah.
This is an extremely
This is a
exact
very
science.
exact science.
What we have learned is that Niles is bit wise and we are bit foolish.
I love that.
Oh, and your friend said that it wasn't as bad as you thought. He already cleaned it up.
Okay, okay.
Just so you know.
Thank you.
Yeah.
Okay.
But it wasn't clean enough to meet my standards because I am a man of more discerning taste.
Okay. Let's go to the last 3 lines of code here.
Yes, please.
Okay. So,
Let's get that big win.
yeah. We broadcasted. We did the XOR. Okay. And now we're doing 2 sets of and nots with this constant. Okay. Now, once again, this top result here, we're deleting the top bit of each nibble. Down here, we're preserving the inverse of the top bit of each nibble. Okay? Now, we take the same constant, this MSB constant, and we subtract this that first result we had. Okay, so why are we doing this? Let's zoom in a little bit. So anytime we have a non-zero value in the bottom 3 bits, when we do a subtraction, it's going to have to borrow from the uppermost bit of each nibble. And so you're going to see a 0 in the result if there were any non-zero bits here. Okay. On the other hand, if we had all zeros, right, what is 8 minus 0? Well, it's 8, right? 8 minus non-zero is going to be 1 through 7, right? And so yeah, that's what we're doing. And so
we're only worried about each individual nibble, not the stream of nibbles. So we're not cascading the.
Yep, and it cannot cascade because we deleted the upper bit of each nibble.
Right.
And so we're doing 8 minus some value that's less than 8.
Okay.
It's going to be 0 through 7. And yeah, if we're doing 8 minus 0, right, we're getting 8. If we're doing 8 minus 1 through 7, we're going to get something less than 8. That's the point. And so yeah, now the uppermost bit of each nibble, it's going to be a 1 if the bottom 3 bits were 0.
Yep.
Okay. And so yeah, you see that in our 2 matches right here. The uppermost bit of all the other nibbles will be 0. Okay. Down here, what did we say before? We're preserving only the top bit, and we're preserving the inverse of the uppermost bit of the nibble. Okay? So, if we AND those two together, right, what we're finding is we're basically checking in the original nibble, was the upper bit a 0 and were the bottom 3 bits a 0? The upper bit was a 0, the bottom 3 bits was a 0. If we AND those, that means all 4 were 0, right? And so that's going to, I don't know if I actually made a result for that one. But yeah, the point is, it's just going to select this match and this match here. And the rest will be zeroed out in the result. We can take the count trailing 0 of the matched mask to say, so yeah, these will be zeroed out. Yeah, I think I didn't put a result in there for this. But yeah, we do the count trailing 0, which will count however many bits this is. So 17. We divide it by, or not 17, or yeah. We divide it by 4, and this will tell us basically how many nibbles came before, which is 4. And then we check, did we match something that's out of range from the number of zeros we saw beyond the bit we're querying for in the gamma coding? If it's out of range, we didn't match anything. If it's within range, we now know the exact index.
Wait, that's a branch.
Yeah, you need a branch to say if we didn't, if it's out of range, then we return null.
And I was starting to think
I know, I'm sorry. I'm sorry.
Yeah.
Otherwise, we add. And then we can look it up in the associated array right there.
Only a SIMD demigod, folks. Demoted to demigod.
Demigod?
Down there with Hercules.
I don't know about that. I don't know. I think this is pretty good. I was actually really proud of myself when I came up with the shift left D algorithm. That was pretty good, so.
In my mind right now, I'm imagining the Niles awarding Niles.
Yeah. You know, honestly, I got to give myself my own awards, you know? So,
It's never Obama giving Obama.
yeah.
It's Niles giving Niles.
Right. That's it.
All right, let's clap on that. I appreciate you using a language that I understand at the very end.
Yes.
That French is way easier to understand than whatever that was.
This is Latin.
It's both.
Okay.
That other stuff was Greek to me. No, so I get some of it, but the only times that I have ever heard someone talk about assembly in my life, other than like one college class where the professor actually taught that day instead of the student assistant, has been the meetups here with you. So it's like you're teaching me Spanish, but instead of teaching me with the Roman alphabet, you're teaching me the hexadecimal representation in ASCII, and then asking me keep along where you've assigned every variable to a Chinese character. So there's 3 or 4 layers of indirection between what I'm familiar with and what you're presenting. And I can follow along to about 2 at a time, but I'm not familiar enough with the base knowledge to follow the whole thing. Like when we went through that first part before you got to the Elias-Fano, like that, I was able to get to a point where, okay, I understand it. And I think that if you had kind of concluded before your optimization, like if you kind of conclude, put in a bow like the Elias-Fano, and then said, but wait, there's more. I think I think I would have gotten the Elias-Fano maybe, but at the end there, you went into the assembly, which I'm not sure if that was necessary in order to understand. And
It's necessary.
well, I don't know if it's necessary in order to understand the Elias-Fano, right? But then that assembly wasn't good enough, so you go into another set of assembly, and you're talking about a specific instruction set, which I'm the least familiar with out of anybody in this room, I think. So, anyway, but I get the high level that you're dealing with a very large data set that's, it sounds like it's not even that sparse. When you're talking about 160 million out of 4 billion, that's scary. That's like y'all are somehow tracking every teenager in America.
Yeah, I don't know. I don't make the data. I just tell them what format to put it in.
Right. Anyway, but that's significant. That's really significant in terms of the number of things you're dealing with. And I'm imagining that the use case for this is cohorts.
Mm-hmm.
And I was going to ask earlier, but then we got around to it of okay, so how? Well, I was kind of wondering how long does it take to update the data? Is it you just run another query? It takes a couple seconds on a SQL database, and then it takes a half a second to update in RAM.
Yeah. So yeah. Again, I don't personally produce it, but we do have some cron jobs that pulls from some database. It puts it into an Elias-Fano encoding, and then we send that to a service which it basically is like Git for our caches, and yeah, once it goes in there, then our live instance can check, is there an update? If there is, it will grab the data and update it and create an index locally. And yeah, it's actually pretty cool how it works. We have like a double buffered system. So we have one thread of the CPU that's checking if we need to update the cache. And then other threads are going to be bidding on ads. And yeah, the idea is while we're updating, we're doing an A/B buffer system. So all of the threads are going to be looking at one, and we can update the other. And then we tell them to switch using an atomic increment. And then next time they go to look for a cache, they say, oh, there was an update. We're all going to look over here. And then I can update this one in the updater thread. So yeah, that's how it works.
Cool.
And I simply optimized that too.
I can't wait to hear more.
No, it's not that crazy. It's just yeah. Every thread owns a slot in an array, and we have spaced it out so there's like 64 bytes between each one, so that they're separate cache lines. So each worker thread owns one of the cache lines, and it can update which increment we're on, like how many times we swap back and forth. And then the worker thread has to check all of them and say, did everybody update to the new one? That way it's safe for me to modify the old one now because it switches. And you can use a VP gather instruction to send out 16 loads in one instruction as opposed to 16 individual iterations of the same loop. So,
Cool. Okay.
yeah.
I know you've shown this last time in another talk, but how are you finding all the ways to instructions that are to the CPU that you're configuring? This is a different set from
So,
no, I understand using it for the Elias-Fano, but let's say I had like a Microsoft ARM, how could I look up the list of instructions for that?
if it's ARM, then my favorite article on that is Whirlwind Tour of ARM by Corsix. He's a really big Lua contributor. And this is a pretty good article that tells you a lot of the things you have. Otherwise, ARM has a website with documentation. It kind of like is not a great website, but you can go on their website and type in instructions and see what they do, or you can look at the list of instructions, see what they do. Another thing is you can go to Compiler Explorer, you can type in some code, and then you can look at what shows up on the right. And so that's another way of teaching yourself if you trust the compiler to pick out the right stuff. There you go.
So, one of the challenges with ARM, as I understand it, is that ARM is a set of specifications for instructions.
Mm-hmm.
So, you're not guaranteed to have like consistency. Different manufacturers of an ARM CPU will implement different instruction sets based on what they're optimizing for, right?
Not really.
Okay, good.
They all have Neon, pretty much. Our MacBooks have Neon. Every server has ARM Neon instructions. There are SVE and SVE2 instructions. And yeah, these ones are not implemented on Apple. But yeah, I mean, I don't.
So
You can't really use these that well, anyways, from Zig. So I actually don't. I just don't care.
Well, because I was thinking in the Raspberry Pi days, there's like, there's so many different specifiers of like ARM, ARM 7A, ARM 6, ARM 5, ARM 5HF, ARM 7, I think VA. Like there's a whole bunch of specifiers. I thought that was related to which packages were available for instruction sets.
Okay, yeah. If
But
you're,
I'm not sure.
yeah, that's my mistake. If you're talking about those like smaller machines, there is more variability there.
Well, I mean, isn't that mostly what ARM is? Well, I guess
I mean-
yeah, like still the iPhone is dwarfed by the other ARM implementations, right?
No, I mean it's not that different from what's in a MacBook. What's on the iPhone?
No. I mean, like when you think of like all the computers in the world, desktops are like 10% or something.
Oh, you mean in terms of numbers? Yeah, yeah. There are a lot of people who are doing single board computer ARM. Yeah.
And so that's what. Yeah, I wasn't thinking
Yeah,
like
sorry,
desktop computers.
Yeah, I was thinking like your phone, your laptop, your server, ARM. All of those ARMs are going to be roughly the same.
Nobody has an ARM server, my friend.
Well, they have them on AWS. You can,
I've run ARM stuff on AWS.
and those do have SVE and SVE2, but
But those they're building on purpose because they're more power efficient, so you can run your Like if you're willing to compile for ARM on AWS, you actually get cheaper because it costs them less in power.
Mm-hmm.
Like,
A question kind of in the similar vein, is like how you have multiple different pop count functions instead of just like using Zig's internal at pop count.
Mm-hmm.
Like, and I'm guessing that's just based on the architecture you're using. That's why you have it. Are you just like scanning through the list of vectorized functions they have, and if they're lacking it, you're making custom versions for that architecture? Or like, how are you making that design choice?
So in the Elias-Fano code, I actually am just using the default pop count
I think you have like
right here. When it came to the masked pop count one in the others the other set of slides, that was a way of just like forcing. Basically, it wraps it in Zig. It wraps it in at select. And yeah, what you could do is you could put a mask on these instructions here, same instruction, or in here, what it would actually do is it would put a mask on these VP move QW instructions. It's probably a little faster to do it this way, but yeah, whatever. I wanted to skip over that detail for the talk, but I am just using Zig's pop count for this primarily. Oftentimes when I do want to do something architecture specific, I'm just doing something with a knowledge of what the architecture will do. For example, on ARM, if I do a pop count of anything, the pop count instruction, it operates on a vector only, and it will give you the pop count of each byte as a result. That's it. You can't ask for anything else. That's all you get. And so with that in mind, I could, for example, take out 8 bytes that are pop counts, and I could multiply by this value to find the prefix sum of the pop counts. So yeah, what I'm saying is like I write code with the knowledge of what the machine will do, but I don't necessarily have to dip into intrinsics or assembly for everything. There are certain things that we don't have facilities for, like that compression, which happens right here. This compressed W, this one does have logic that specializes based on the hardware, because this is one instruction on AVX 512. On anything else, not really. You have to emulate it with a table lookup and a general purpose vector shuffle. See ya.
adios. All right, well, I'm going to go ahead and stop the stream. Thanks again for enlightening us.
Mm-hmm.
Adios, everybody online. And
Would you suggest for, because I know
that's
you
it.